Okay, so in our lab, we learned that the Earth does not absorb enough energy, enough heat to keep it from freezing, and yet the Earth is not frozen, right? So we said that this is caused by something called the greenhouse effect, and this video is dedicated to understanding the greenhouse effect. Greenhouse effect is probably the most important concept that we're going to talk about in this climate change section of the course. It forms the foundation of pretty much everything else that we're going to talk about. So it's very important. And to first understand the greenhouse effect, we're going to have to learn a little bit more about the energy that's coming out of the sun. Okay, so all energy in the universe is characterized by a spectrum. It's a spectrum of energy that we call the electromagnetic spectrum. So the electromagnetic spectrum is the total of wavelengths of energy. Okay, so by wavelengths, we should know that that all energy has the properties of a wave, right? So here we can see sort of a schematic waveform here, and you'll notice that its wavelength is getting longer from left to right on this diagram. So by wavelength, we sort of mean the physical distance between peaks or troughs in a waveform, right? So both these distances are identical. This is the wavelength of a wave. Sometimes you'll see wavelength annotated with the Greek letter lambda. Okay, so there's many different kinds of electromagnetic energy, and we're actually pretty familiar with most of them, right? So the different kinds of electromagnetic radiation or energy are differentiated by their wavelengths. And so the longest wavelength kind of electromagnetic energy or radiation are radio waves, right? So radio waves, the same stuff that comes out of our car radios. And these basically have very long wavelengths, or on the long wavelength side of the spectrum. And so the wavelengths of radio waves are essentially like meter scale, right? So a meter is a little bit less than a yard. It's about 2.5 feet, right? So long wavelengths on the scale of meters. Microwaves, right? The very same kinds of waves that are used by our everyday kitchen appliances. Microwaves are a bit shorter, right? They are on the sort of centimeter to millimeter scale wavelength. So getting shorter wavelength. And then the next kind of energy is called infrared. Okay, so infrared energy. So infra means below. And then red is the color red, right? So below red energy. Infrared energy is called infrared because it's the kind of energy that's got wavelengths that are just longer than the visible spectrum, right? So visible light is only a small band of electromagnetic radiation that human beings have evolved to be able to see. And so we know that visible light's, made of a bunch of different colors, essentially the colors of the rainbow, right? Sort of from red, to yellow, green, blue, and all the way up to purple or violet here. And so basically visible light has this very narrow band of wavelengths. Okay, so visible light has a wavelength that's somewhere between about 400 to 700 nanometers. Okay, so a nanometer is 1 billionth of a meter. 1/1000th of a meter. Okay, so red light has a wavelength that's about 700 nanometers, and violet light has a wavelength that's about 400 nanometers. So as we move from red to violet light, the wavelength is getting shorter. So the wavelength of energy is getting shorter. Now, this length of the wavelength of energy determines whether that is a quote high or low energy form of radiation. Okay, so okay, radiation with long wavelengths is called low energy radiation. Radiation with short wavelengths is called high energy. Right, so as wavelengths get shorter and shorter, we're going towards the higher energy spectrum of electromagnetic radiation. All right, and so if we think about the other high energy forms of radiation, we're also familiar with all of these. So ultraviolet radiation, called ultraviolet because ultra means above, right? So it's higher energy than the highest energy form of visible light, which is violet light. So ultraviolet, above violet, is the kind of energy that comes out of the sun that gives us sunburns, right? It's UV radiation or ultraviolet radiation that damages our skin, like this poor surprised-looking person who didn't put on sunblock. And then if we go to the next higher form of energy, X-rays, right? These are the very same X-rays that sort of tell us whether or not we've broken bones. And if you've ever been X-rayed, you know that the person who does the X-ray goes and stands behind a cement wall, and they put a vest made of lead, basically a bulletproof vest, onto you to protect you from the energy, right? Because it's high energy radiation, and too much of it can harm you. And if you get to the very highest form of energy, right, the very shortest wavelengths, it's called gamma ray energy. And this is basically, nuclear danger, atomic, superhero kind of radiation, right? This is the radiation that made Bruce Banner turn into the Hulk. So this is sort of the realm of superheroes and nuclear bombs and the apocalypse, right? Very, very damaging, very high energy radiation. Okay, so these are our different kinds of radiation. Again, we've got radio waves, long wavelengths, sort of meter scale, microwaves, sort of centimeter to millimeter scale. Infrared radiation has about a micron scale, so this is about 1/1,000,000th of a meter. The visible light spectrum is between 700 and 400 nanometers. Again, nanometers are 1/1000th of a meter. And then as we go up higher into X-rays, we're getting into really, really, really short wavelength radiation here. Sort of less than a nanometer, or getting into what are called picometers. Which are 1 times 10 to the minus 12. This is trillionths of a meter. And then gamma rays have wavelengths that are so short that they're even called femtometers. And those are wavelengths on the order of 10 to the minus 15. So I don't even know what's above trillions, right? But really, really small wavelengths. Okay, and so again, we've got sort of experience with all of these. Now, I didn't mention this middle picture. Perhaps some of you will recognize this as a shot of Arnold Schwarzenegger from the 80s classic Predator, right? So in this sci-fi movie, the Predator is this alien from outer space, and he has fancy, goggles, a part of his helmet that let him see the body heat of Arnold Schwarzenegger and all the other Marines out in the jungle, right? So infrared energy is commonly thought of as heat energy, right? So the predator has these infrared seeing goggles, right? And so this is a very important concept, that this sort of heat energy that we call infrared, right, below red energy, it exists, and it's radiating out from all things that have, you know, a certain temperature, but we can't see it, right? Human beings cannot see anything with a longer wavelength than about 700 nanometers and a shorter wavelength than about 400 nanometers, right? We actually can only see this very narrow band of energy. But that doesn't mean that infrared energy doesn't exist. It does exist, and it's very important. It's heat energy. So if you think about the expression, something that is red hot. Okay, so all things that are, you know, warm, or sort of like Arnold Schwarzenegger here, are giving off energy, and it's infrared energy. It's below the point where it would actually have a wavelength short enough that we could see it. But as things get hot enough, they start to glow, right? And so the expression red hot means that, hey, something has gotten hot enough that it's actually going to start to glow. And the first color that it's going to start to glow as it goes from infrared to sort of violet infrared to red, just visible radiation. Red's the first color. That's why things glow red hot. And then if something's really, really hot, you might have heard the expression white hot, right? So white is, of course, the color of all these different colors combined, right? That's what rainbows are, is scattering of white light to break up into its different wavelengths. But if something is glowing hot enough, then it's actually white hot. It's emitting visible light. Okay, so the energy that's released by the sun is mostly visible light, right? So this is a plot showing spectral irradiance, right? So how much energy and what its wavelength is that the sun is emitting. So you see this sort of peak shape right here, and then sort of a slow taper down like this. And here is a wavelength on this axis. Okay, so this is longer wavelengths, so lower energy, right? Lower energy, things like microwaves, and then kind of ramping up here. All of a sudden we hit about 700 nanometers right here, the visible light spectrum between 700 and 400 nanometers. And we can see that most of the energy that's reaching the surface of the Earth, right, that's coming from the sun, most of that is in the visible spectrum, right? And that's why human beings have evolved to see it, right? Most things have evolved to see visible light because it's the most abundantly available kind of light. All right, but then we also see that there is some amount of energy that's sort of ultraviolet light, right? This is the energy that's going to give us sunburns and skin cancer, right? So it can be damaging because it's higher energy. It's got that shorter wavelength. But most of the sun most of the energy from the sun is in the visible light spectrum.